Is my slide visible? Yeah. Okay. Thank you for waiting. There was some technical issues where I couldn't record my screen. So yeah, sorry for the delay. So let's start today's tutorial. So today I have prepared around 30 questions. Again, this basically deals with magnetic resistance, GMR, AMR, and CMR, and along with the ferrofluids, some ideas about the ferrofluids. So this is an online tutorial session for the NPTEL course, Physics of Functional Materials and Devices. So this is a course which is currently taken by Professor Amreesh Chandra from the Department of Physics, IIT Kharagpur. So basically from the title itself we can understand that this course is mainly focusing on the functional materials, which means materials that has a that has multiple functions, not just one function, but it has multiple function. And we are not just limited to the material aspect, but we also deal on the device aspect. How do we fabricate the devices with this specified materials? So uh, just a second. Yeah, I'm Rahul R. I'm a Prime Minister's Research Fellow from the Department of Physics, IIT Kharagpur. So this is my email ID. You can contact me if you have any doubts regarding the questions that is being shared or any questions regarding uh, the yeah, whole assignment and this online tutorial sessions. So let's not waste the time. So the first question for today's session is: the phenomenon where application of a DC magnetic field changes the resistance of a material is known as ferromagnetism, magnetoresistive effect, piezoelectric effect, superparamagnetism. Just think for a while, then we'll discuss the answer. Yeah, it is obvious that we have learned about all the other three. We know what is ferromagnetism. We know what is piezoelectric effect. Piezoelectric effect basically when pressure is applied, that will create some kind of electric field. So some kind of relation between the electric field and the pressure is nothing but the piezoelectric effect, and we know superparamagnetism, which is a kind of a magnetism that is observed in nanoparticles. And yes, the correct answer is magnetoresistive effect, where we can see a change in the resistance of a material when an external magnetic field is applied. Okay, okay, fine. Why it is said as a DC magnetic field? Because AC magnetic field is a fluctuating magnetic field. The North Pole and the South Pole uh, just changes. It will just switch at certain frequency. So here the North Pole and South Pole are fixed, and then therefore it doesn't change. Okay, different. So the correct answer is magnetoresistive effect. Two ferromagnets are separated by few atomic layers of insulators are generally named as garnets, colossal magnetoresistance, giant magnetoresistance, tunnel magnetoresistance. So the idea is it's separated by few layers of insulators. What is it? Yeah, insulators. See, insulator needs to be non-magnetic resistor. Okay, okay, that is fine. We are not going into that deep. We are just looking for the what you get from this answer is the major thing to, as I said, to notice is okay, it can be non-magnetic also, that is true, but we are looking for the other ideas, which is like what is this colossal nitrogen and nitrogen tunnel nitrogen. So as you said, the correct answer, just a second, correct answer to this question is option D. Just a second. Okay. The correct answer to this question is tunnel monitor system. In Jan monitor system, we generally take a single layer, right? Then we take a single layer. Hmm? Okay, so the correct answer to this question is tunnel magnetic resistance. Okay, yeah. This is the tunnel magnetic resistance. This is I'm having some technical issues today. Yeah, already this has been discussed. Yeah. In which year the giant magnetic resistance was first discovered? Any idea? In which year was it discovered? In which year? Jan, it is difficult to remember all the years, but since we are primarily focusing on this, it is these kinds of questions can be asked on your examinations also. The correct answer is I think it is 1988. It's 1988, option B, I guess. Yes, correct answer is option B, 1988. Yeah. So basically, this was discovered Albert and Peter Grunberg. So and they were awarded Nobel Prize in 2007 for this particular discovery. Okay, this is kind of a very important concept when we come into spintronics and other magnetor resistive storage device. We have this hard disk, and basically this discovery was very useful for this kind of technologies. Even now, there are a huge research happening in this field where people actually deal with this GMR, CMR, and AMR, and they are trying to get very high. We need to have a very slight variation in magnetic resistance, and then we need to have a high response, high change in the resistance. So these kinds of a material will help us to discover or invent better or high performing um, spintronic devices. So basically, yeah, this uh, so this has been awarded as a Nobel Prize because it is a very important discovery. Okay. Which among the following is an example for a GMR material? Fe2O3, FeS2, FeCl, Fe3O4. Yeah, okay. So the correct option is, as you said, the answer is C, FeCl. So what happens here? So here you can see that um, it consists of basically alternating layers of ferromagnetic ion. So ion is basically the ferromagnetic substance and the non-magnetic chromium. Here the chromium acts as the non-magnetic medium. So the GMR effect basically arises from the interaction. Okay. Basically, we have seen that in the lecture, right? It basically comes from the interaction between what? The magnetic moments in the magnetic layer, which is the iron layer, and the non-magnetic layer, which is the chromium layer. Okay, and this lead to a significant change in the resistance. We know we are talking about this magnetic resistance, so there is a significant change in the resistance, electrical resistance. Okay, it's not any other resistance, basically the electrical resistance that experience a change. Okay, so we have a layer of iron. So for Fe3, yeah, we'll have a layer of the material is a layered material, and we have a layer of iron, and we'll have a layer of chromium. So this is a layer of chromium. So this is the magnetic layer, particularly the ferromagnetic layer, and this is the non-magnetic layer. Again comes the, so basically this will act as a GMR multiplier. Okay, fine. Let's move on. The most used and popular method for fabricating magnetic thin films are magnetic process, sputtering process, slicing process, cutting process. Which one do you think is the commonly used technique for creating magnetic materials? So generally we use sputtering process. Okay, use sputtering process. What is sputtering process? We'll have a the magnetic material will be our source material. Source material. And what we will do? We will fire ions. Okay, charged ions. We we will like we will just bombard the source, which is our magnetic material. Magnetic material. We will bombard this with ions, and this will like if you will just clear this magnetic material, and we will keep a substrate. So this will be a substrate, and then these particles will come and get deposited in the substrate. Okay, the deposition happens. This is a basic sputtering process. There are different kinds of sputtering. Okay, the it is a very frequently used experimental techniques where we have to make films. Okay, film. If you have to make a film, what is film? Film is a layer of material that has a very the thickness is in the few nanometer. Okay, and there will be a very finite thin uh, coating of a material. Okay, that is basically called as a thin film. Okay, so we can create these types of thin films of all this sputtering process, and this is a very frequently used techniques. Okay, recently researchers found anomalous giant magnetoresistant in which form of the carbon-based material at room temperature. Activated carbon, carbon microsphere, graphene, carbon nanosphere. Yeah, it is graphene. So graphene is a single layer carbon material. Okay, it has a structure of hexagonal carbon. So the structure will be something like this. We have an array of hexagonal carbon. Okay, so this how do we get graphene? The one of one of the easiest way to make graphene is we have graphite. Graphite is easily obtained. We have a so suppose this is a graphite. We will stick a scotch tape. Okay, okay. This is tape or scotch tape, and we just stick that on the surface of this graphite. So this is graphite. We just stick on the surface, and then we'll just deep, and we'll get a layer of this material, a few atomic layer of this material in the scotch tape. So it is very difficult to peel off a single layer, but it has very few layers. So ideally, the single layer of graphite is called the graphene. So this is a very commonly technique. The other technique is the other commonly technique. So it is very difficult to produce pure graphene. Okay, so this is the pure graphene. So it is very difficult since this being a class where we discuss the experimental procedure also. Let me briefly explain how do we create graphene or how do we synthesize graphene. Okay, so this is a pure graphene structure, but it is very difficult to fabricate, or it is very difficult to synthesize these pure graphene structures by some chemical methods. So what we do, we create some kind of structure which has some kind of there will be some kind of functional groups attached to this. So it is called the graphene graphene oxide. So one way, so graphene oxide is a graphene with some kind of functional groups attached to it. So what we do it practically in most of the cases, instead of just directly synthesizing graphene, we go for graphene oxide. How do we create graphene oxide? We do that by using some technique called modified Amreesh method. This is a very frequently and very commonly used techniques to create graphene oxide. What we do here, we take a solution containing 9:1 ratio of HNO3, HNO3 and H3PO4. For example, we take 45 ml of this and 5 ml of this. It will be taken in the ratio of 9:1. To this, what we do is like we add graphite powder. Okay, we have graphite powder. This powder is added to this, and there are multiple variations. Some people add sodium nitrate NaNO3 also to this. So basically, we take this solution, we add graphite powder. Okay, and now we keep on stirring the material, and then we'll take it to ice bath. We will maintain temperature at a certain degree, and then we will slowly add potassium permanganate, which is KMnO4, and we stir that solution for a stipulated amount of time, and then we'll add um, H2O2, which is hydrogen peroxide dropwise. Before that, we can add water also to dilute the thing, because see, KMnO4, potassium permanganate, is a material that is used to make explosives. So it is very dangerous to work with highly concentrated KMnO4. Okay, so and you are adding an oxidation agent, oxidative agent, which is H2O2. H2O2 consists of a huge number of oxygen in that. So if we just directly add KMnO4 H2O2 to a solution of highly concentrated KMnO, it is high chance, there's a high chance of explosion. So what you do is that you dilute the solution by adding some deionized water, and then you dilute the solution, and the solution contains HNO3, H3PO4 and graphite powder and KMnO4. So that solution you dilute. For example, if it is like 50 ml of solution, currently you have 50 ml of solution, you add around 150 ml of DI water, and you make it a very dilute solution, and then you start adding the H2O2. That will actually stop the oxidation. So H3 KMnO4 is a oxidative thing, and after adding, the whole oxidation process will gradually stop when you add the um, H2O2, and it should be added very carefully in drop by drop manner, because you can, if you add it quickly, like if you start pouring H2O2 as a whole, you can see actually the fire comes out of your solution. Okay, so it is very dangerous to work with, but you add it slowly, and then you can see that the solution turns its color from, so when you add KMnO4, the color would be like dark green. Okay, so when you add H2O2, you can see that there is some kind of reaction happens, and the solution will become yellow in color. That is the uh, that is the point where you can see that a graphene oxide has been formed. Now what you have? You have a graphene oxide. So graphene oxide is graphene with some kind of functionalizations into the material. But you need graphene. How will you get graphene? One of the easiest method to get reduced graphene oxide, we call it as RGU. So you remove many of the functional groups in that, and you make it make it a more pure graphene. So for that, what you do, you take this graphene oxide powder, you keep that in an argon atmosphere, and you heat that substance for around 500 degrees Celsius for say 10 minutes. 10 minutes is more than enough, and then you can see that most of the functionalization will be removed, and you will get almost pure graphite. It's not exactly pure graphite. Still, there will be some kind of functionalizations, but it will be less than that of graphene oxide. So that is a technique where you can create reduced graphene oxide. So this is an experimental way of you create graphene. Okay. So yeah. So with this particular material, and this material has very interesting properties. One is it exhibits GMR at the room temperature, and it is also very highly electrical conductive material, and it is very tremendously used material. It has applications ranging from physics to chemistry to even civil engineering applications. You can see that nowadays people are using graphene oxide as a substituent of cementitious materials. So that because graphene oxide has a very high surface area, and that can be used in certain applications where which will give you higher resistance to certain atmospheric conditions like acidic nature. Okay, okay, fine. So is that the case? Then we'll move on to our next question. And the next question is, yeah, today's hard disk drive, which one of the following is used to store information? Pattern of the voltage, pattern of the current, spin of the electron, spin of the neutron. Just think for a while, then we'll discuss the answer. Just think for a while, then we'll discuss the answer. Yeah, okay. There is a question here. Okay, what is anomalous GMR effect? Okay, so uh, basically GMR and AMR are kind of magnetic resistance that we can observe, but they basically differ in their working. Okay, they basically differ in their mechanism, how they work. Okay, so uh, the major difference that we can say is that GMR basically lies on the alignment of the magnetic moments in ferromagnetic layer, where uh, anomalous GMR involves some kind of spin orbit interaction. So it is a lengthy thing. It is very hard to difficult to explain the entire thing uh, at this point. So yeah, I can now just say that the GMR effect basically comes from the interaction between the magnetic moments in the ferromagnetic layer, but anomalous GMR has some kind of spin orbit. The spin and orbit interactions will come into play. Okay, but in GMR it is just moments, the interaction between moments in the layers of this GMR material. We know there is a magnetic layer, there is a non-magnetic layer, and the interaction between the magnetic moments in these layers is resulting in the GMR, whereas in anomalous there is an interaction between the spin and orbit. There we have a spin magnetic moment and the orbital magnetic moment. The interaction between these two will give you an extra factor, and that will give you the anomalous GMR. Okay, so it is difficult to explain the entire thing and at this point of time. So yeah, yes. So the correct answer is spin of electron. Yeah, okay, that's the correct answer. Now comparing GMR, somebody has to join. Yeah. Um, Comparing GMR, which is a giant magnetoresistance, and TMR, which is standard magneto, which is not an advantage of TMR as a read head. We are having a read head, which is basically we use that in the reading the data in a hard disk. Okay, so what is the advantage given in this, which is not an advantage? I mean, yeah, yeah. Let's go through the options. Then discuss the idea. Correct answer is TMR is larger in size. So I mean the wrong answer. Yeah. So this is the option. Basically, it is should be smaller inside. Okay, TMR is basically more stable in magnetic performance. Why? Because the change in the resistance. Okay, when we apply magnetic field and when magnetic field is not applied, so then there is a change in resistance that will happen, right? So that change in resistance is very high in for TMR materials. Okay, and the energy consumption for TMR materials is, yes, it is low when compared to GMR material. Also, and as the so there's a high shift in the resistance, you can see that the signal to noise ratio is much lower in that case of TMR. Whereas in GMR, we don't get such a huge change, but as compared to TMR, and hence when compared to TMR, this signal to noise ratio is comparatively high. And we are comparing to TMR, GMR is less stable. The magnetic materials which plays as GMR are less stable when compared to that material which exhibit TMR properties. Okay. Ferrofluids are suspended in liquid. Generally can be called as liquid magnet, solid magnet, dispersed magnet, none of them. Yes, definitely. They are classified and they can be called as liquid magnets. Okay. Okay, fine. Which among the following does not belong to the characteristic of ferrofluid? High electrical conductivity, ability to flow like a liquid, formation of unique patterns in magnetic field, superparamagnetism. Which among the following need not be a uh, property that belongs to the ferromagnetic or ferrofluids? Yes. Remain is the correct answer. They need not have very high electrical conductivity. Yes, they will flow like a liquid. Yes, they will form some kind of patterns when it is exposed to magnetic field. And yes, they show superparamagnetism because we generally suspend nanoparticles, nanomagnetic materials into some kind of a fluid to get these kind of superfluids. Okay. What is the purpose of using ferrofluids in speakers? To make speakers colorful, to cool the speaker components, to generate light, to improve the sound quality. Which one do you think is the correct answer? D, to improve the sound quality. Okay. Any other suggestions? So, yeah, it is like indirectly connected to the improvement of sound quality. The correct one to say is it will basically cool the speaker components. Okay, so the best answer among this is to cool the speaker components, and that will eventually lead to improvement of the sound quality. So what does ferrofluid do is that they cool the speaker components. So when there is some kind of vibration happens in the speaker, that will eventually heat up the whole speaker system, and then that will eventually lowers the performance of the speaker, which means that the sound quality degrades. But when you use this ferrofluids in speakers, it was found that it can exhibit very high heat dissipations. So that means that the heat generated in the system can be taken out by using these kinds of materials, and that will be helpful and that will improve your sound quality. So the correct answer is option B. Okay, and option B will lead to option D. So when such a question is asked, you are supposed to write option B. Okay, what type of memory utilizes spintronic principles and is known as fast access times and non-volatile nature? Flash memory. No, it's not flash memory. It's option B. Option A, optical memory. No, it's not optical memory. It's basically MRAMs. Okay, that is magnetic random access memory. Okay, MRAMs generally use spin-rolling principle to store data. So in our computer we have RAM. Why do we use RAM? We have a hard disk and we have a RAM. Okay, hard disks are devices where we store data for a huge longer period of time. And the data is accessed at a slower rate. So it is difficult to access your data compared to that of your RAM. So in RAM, it's like random access memory. You need quick response. So you need to get data. So suppose you are working on some kind of a software and it will be running. Okay. So during that running time, it need to access some data and that access time should be minimized. And if it is stored on the hard disk and if we are depending only on hard disk and that will take a huge amount of time. Okay, it all happens in a split of a second. It does in a very minute second. So we use RAM and especially we use my MRAMs and MRAMs we use this spintronic principles. Okay, spintronic sensors are commonly used for detecting which of the following: temperature, pressure, light intensity, magnetic field. Yeah, should be magnetic. Yes, it is very easily. It can be. See, basically, it sends the magnetic field. Which spintronic device is commonly used in hard disk to read data from the spin wall, spin transistor, spin capacitor, none of them. Correct answer is option A. Spin wall is a kind of devices that is generally used to get data from the hard disk. Okay. So this is the 16th question. Which of the following is not a model for giant magnetoresistance or GMR? Alternate layer of non-magnetic and oppositely magnetic magnetized ferromagnetic material, randomly oriented single domain of ferromagnetic cobalt particles in non-magnetic copper matrix, hybrid system of copper nanoparticles in a silver matrix sandwiched between nickel ferrite magnetic layers with alternate magnetization, a single layer of ferromagnetic material. We use a read head uh, reading on the yeah, so the read head, so we have seen that the read head also has this magnetoresistive properties. Okay, so basically that also works on this magnetoresistive property. Hard disk works on the magnetoresistive property of the material. It stores data by changing the spin or the polarity of the spin of the system. That will give you zeros and ones, and then it stores the data. And the working of the spin, the header is basically based on the spin ball. Okay. So this is the 16th question. So we in this we have Sir has discussed various models for this GMR in his lectures. If you remember, which of them, which of the following is not a model for this GMR? Yes, I'm seeing some answers. Yes, the correct answer is option D. So all the mentioned above, these are the three models that was described in the lecture. And yeah, we all know that. I think you have gone through the lectures, and these are the three models that was used. Okay. So in a system where electron scattering depends on the orientation of electron spin with respect to magnetization, what happens when a DC magnetic field is applied into parallel layers? The magnetization of the magnetic layers become aligned in the same direction. Electrons with spin align opposite to the magnetization are scattered more strongly. Resistance of the material is determined by the lower resistance spin channel. All of the above. Which one do you think is the correct answer? Yeah. Option D is the correct answer. Because the magnetization of magnetic layers become aligned in the same direction. That will happen, that is being tried to happen when there is a magnetic field. The electrons with spins aligned opposite to magnetization are scattered most from yes, that also happens in the system. The resistance of the material is determined by the lower resistance spin channel. Yes, the the resistance of the material is determined by the channel that is formed by the lower resistance spins. Okay, so that is the channel. Higher the lower resistance spin channels, then the higher is the resistance. Okay. I mean, lower is the resistance. Okay, so the correct answer is all of the materials made of single domain ferromagnetic nanoparticles embedded in non-magnetic matrix exhibit giant magnetic resistance. How does applying a DC magnetic field affect the resistance of the material? It increases the resistance. It has no effect on the resistance. It decreases the resistance. It first increases and then decreases the resistance. Which one do you think is the correct answer? I'm saying option D. So the correct answer is it's option D. It decreases the resistance. By applying the application of the DC magnetic field will basically rotate the magnetization vector, the ferromagnetic nanoparticles, parallel to the direction of the field, and that will reduces the resistance. And we are basically focusing on the ferromagnetic materials. Okay, ferromagnetic material. So by this, it will we can see a decrease in the resistance. The correct answer is option C. Okay. Hybrid system exhibiting magnetoresistant properties of consist of metal nanoparticles embedded in a non-magnetic matrix, magnetic nanoparticles embedded in a non-magnetic matrix, non nanoparticles embedded in a metal matrix sandwiched between metal magnetic layers, metal magnetic layers sandwiched between metal nanoparticles. Which one do you think is the correct answer for a hybrid system? Can give you a hint where we have discussed one example with silver and purple. Yes. Yeah, I'm seeing some answers. That's great. See the answer. The correct answer is yes. Option C. So this was explained in the class, right? We have this silver, and in the silver layer, which is a metallic layer, in that we have dispersed some cobalt nanoparticles, and that is being sandwiched between nickel ferrite. That is the ferromagnetic material or the magnetic material. And this is an example for the hybrid system. Okay, the phenomenon should be the phenomenon of magnetoresistance in metals is primarily observed under which conditions? Low magnetic field and high temperature, high magnetic field and high temperature, low magnetic field and low temperature, high magnetic field and low temperature. Which one do you think is the correct answer? Okay, I'm seeing multiple answers. Yes, it is high magnetic field and low temperature, and that is the major drawback of these techniques. See, most of the time what we are seeing is that we need high magnetic fields and low temperature to observe this kind of matter resistance in metals, and that makes it very difficult to use them practically. Suppose you have to cool the materials to -20, -25 degrees. It is very difficult to maintain that, and then you use it for some applications. What is the ideal thing that you need? You need a material that works on low magnetic field and at low low temperature, but ambient temperatures. Then that is a very good thing for you. If it is working at say room temperature at 25 degrees Celsius, it is working very well and good at comparatively low magnetic fields. Then it is very fine. You don't need Tesla's of magnetic field to see such kind of a phenomenon. Then that is well and good. You need only few gauzes of magnetic field. Okay. Magnetoresistant effect becomes evident only when the magnetic field is strong enough to curve the electrode trajectory within a length equal to its mean free path, Bohr radius, deviate length, Fermi length. Which one do you think is the correct answer? You can expect these kinds of questions. See, the most of the questions are also taken from the previous year assignment questions. And you can expect similar kind of questions on your examination as well as current assignment questions. So you can see the level of questions that will be asked for the examinations as well as the assignments. So this, yeah, definitely I think these questions will be helpful for your assignments as well as examination. Yes, I'm seeing some answers. It is mean free path. Now let me ask you, what is mean free path? Any idea what is this mean free path? Any idea? You can just type on the screen. Yeah, that is the thing. So if you see an electron moving, okay, so average distance it moves before any two consecutive collisions. So, okay, if it goes from here to here, and no collisions happen between, this is point A and point B. No collisions happen between these two positions, and if it just crosses B, then the collision happens. So we can say that the average length, average distance between two successive collisions, the path it has traveled between two before the collision, average path it has traveled before a collision is basically its mean free path. Okay. Matter with reference to GMR, consider the following statement. Magnetic resistance is the tendency of a magnetic material to change the value of its magnetic resistance. GMR is used in hard disk drives. Which of them is a correct statement? Which have got answer correct? This question I think was asked on. This question I think was asked on uh, one of the civil services examination. Yeah, okay, I'm seeing an answer here. the options carefully and then answer. What? Okay. If we tell you the correct answer is option 2 only. Why? Because it is, we are talking about the magnetic resistance. It is not the magnetic, it should be the electrical resistance. Okay. So basically we are changing the electrical resistance by changing the magnetic field. Okay. So the correct answer is option 2 only. What is the primary purpose of surfactant coating on magnetic particles in ferrofluid? Enhance the magnetic properties of the particles to prevent particles from clumping together, uh, to increase the viscosity of the ferrofluid to reduce the overall weight of the film. Seems not answers. See multiple options. Yes, the correct answer is to prevent particles from clumping together. So this is important. Why? Because or else the particles will just stick together and then we cannot observe the ferrofluid nature anymore. So yeah, the correct answer is option B. Okay, let's move on. Which of the following is commonly used? Is a common example of ferrofluid. Iron filling suspended in water, nanoparticles of magnetite suspended in oil, sand mixed with water, copper sulfate solution. Yeah, correct answer is option B. Nanoparticles of magnetite suspended in oil. So that is the correct answer. We all know why the others are not correct. This will not give you a ferrofluid material, and definitely this won't give you a ferrofluid. And this is not also the copper sulfate solution is also not a magnetic material because copper is a magnetic material, but when it is attached to oxygen, it is not a magnetic material. Okay, okay, fine. So let's move on. Let's move on to the next question. Ferrofluids were initially developed to create magnetic field dependent on isotopic optical properties, control fluids in space, inhibit clumping in particles, change their density in proportional to magnetic field. What was the reason for inventing this ferrofluids? Okay, some option. Okay. The correct answer is option B, control fluids in space. So basically, this kind of material was discovered in NASA. So they used to control their space fuels or the rocket fuels in space. Okay. So this was invented by NASA. This was one of the discovery by NASA, and yeah, it was initially used to control fluids in space. It was also used to get high performing speakers that we have already seen. Who is credited with developing the first ferrofluid? Stephen Papel, Nikola Tesla, Albert Einstein, Marie Curie. B, A. Another option. Option A. B. The correct option is Stephen Papel. Stephen Papel was a NASA scientist and he So this is Shrikant Apple. He discovered the ferrofluids. Okay. How do ferrofluids respond to magnetic field? They become less dense. They change their color. They become more viscous. They change their density based on the field strength. So when do you think is the correct answer? Yeah, correct answer is option B. They change their density based on the field strength. Okay, that is the correct answer. The effect described where linearly polarized light emerges as elliptically polarized light due to the application of DC magnetic field is known as Faraday effect, Zeeman effect, photoelectric effect, Cotton-Mutton effect. This is important because this question basically defines what is Cotton-Mutton effect. So it is option D. So option D. So this in Cotton-Mutton effect, what it happens is that linear polarized light will emerge as a elliptically polarized light when a DC magnetic field is applied to a material. Does it changes the refractive index of the material? Yes, that can also be changed. The refractive index of the material will also be kind of modified when the magnetic field is on, because it basically changes the orientation of the spin, and that can change the optical properties of the material. Yes, refractive index of the material can also be changed. So refractive index is a material property, and that will change on various factors. Even if you make the material very thin, and that can even affect your refractive index. Okay, so that's it. What technique can be used to decrease the spin polarization of either electrons or the centers of spin diode? Magnetic resonance imaging, electron spin resonance, nuclear magnetic resonance, X-ray diffraction. Yeah. Electron spin resonance is the correct answer. Okay. So I think these are the 30 questions for today. So there are a few people who are joined. Negative refractive index. So refractive that I have to check. Just a second. Let me check. Okay. Yeah, I have to check that. I'm basically not working on particularly on the uh, optics, so I'm not very much familiar with this negative refractive index. Okay. There are few members who have joined the class a bit late, so let me discuss the questions quickly. What are the questions that we have discussed today? So yeah, the first question that is we described was the phenomenon where the application. So let us just quickly revise all the 30 questions that we have just seen. So we have already completed for the so the people who have just joined right now, we have already completed the discussion on 30 questions. So since you are just joined for the course, for the class, let me just quickly go through the questions that we have discussed on today's class. First question was a phenomenon where the application of a DC magnetic field changes the resistance of a material is known as, it is basically the magnetoresistive effect. Okay. Next question. Two ferromagnets are separated by a few atomic layers of insulator are generally known as, it is basically the tunnel magnetoresistance. Okay. Okay. Two, again it's the same question. In which year the giant magnetoresistance was discovered? So it was discovered 1988. Okay, so this was discovered by Alfred and Peter Gunberg. So both of them together received the Nobel Prize in 2007 for this particular discovery, and this has a huge applications because it is a very fundamental basic of our computers and other storage, even our mobile phones. The storage technologies of our mobile phone started emerging after this discovery. Okay, so all the storage applications basically started after the discovery of this GMR. Before that, we have this some optical storage devices, and that has its own limitation. It is limited by the amount of data that can be stored, and also the speed at which we can extract data. So yeah, so GMR effect was discovered in 1988. Okay, so which among the following is an example of GMR material? Uh, if you see here, it's basically the uh, is the material that exhibits this CMR property, because here we have a magnetic ferrous and a chromium which is non-magnetic in nature, so they are in a sandwich band, so it basically acts as a GMR material. Okay, so others are not GMR material, and then doesn't, because it doesn't show the GMR property. Okay, so what is the most commonly and popularly used method for fabricating magnetic thin film? So thin film is a very finite, it basically consists of few nanometers of material. So the majorly used technique to create magnetic thin films is sputtering process. In sputtering, we use charged ions that will be bombarded on the material surface. Here our source material, which is the material, is a magnetic material that has to be deposited over some kind of substrate. So the ions will be bombarded on the material, and then it will create some, it will just eject the material out of that, and that will get deposited on certain substrate, and the deposition is very uh, limited to few layers. So we can have a control over the thickness of the material here. By there are multiple factors how closely you keep this substrate to that source, and how long you expose the material substrate. By controlling all those things, we can actually control the thickness of the deposition. Okay. Recently, researchers have found anomalous giant magnetoresistance in a form of carbon-based material at room temperature. So it was discovered for graphene. So graphene is a single layer graphite material. Okay. In today's hard disk, which of the following is used to store information? So basically, the information is stored based on the spin of the electron. Okay. Comparing to GMR and TMR, this is not an advantage of TMR. The TMR size is actually smaller. So the correct answer is option B. It is said that it is larger, but it is actually smaller. So the correct answer is option B. Ferrofluids are suspended in a liquid, generally can be called as liquid magnet. Okay, so ferrofluids are generally called as the liquid magnet. Okay, which of the following does not belong to the characteristic of ferrofluid? High electrical conductivity. That doesn't need to be a characteristic of ferrofluid, because basically we are yeah, we'll come to that later. So this is the high electrical conductivity is not a characteristic feature of ferrofluids. Okay. What is the purpose of using ferrofluids in speakers? The major use is to cool the speaker components, and we can say that it also improves the speaker quality or the sound quality, but that is an effect of option B. Option D is an effect of option B, because as we cool the speaker components, then it will improve the sound quality. So the best answer is option B. What type of memory utilizes spintronic principle and is known for its fast access times and non-volatile nature? It is NRAMs. What is this non-volatile nature? It means that your information is not lost even if you turn off the uh, electricity or power. Okay, so NRAM is the answer. Spintronic sensors are commonly used for detecting which of the following? It is basically used to detect the magnetic field. Which spintronic device is commonly used in hard disk to read data from disk? So the commonly used spintronic device is spinwall. Okay. Which of the following is not a model for giant magnetoresistance or GMR? So the correct answer is a single layer of ferromagnetic materials. That is not a way of describing GMR. All the other three are three different models which was explained in the lecture to describe the GMR. In a system where electron scattering depends on the orientation of the electron spin with respect to magnetization. What happens when a DC magnetic field is applied parallel to these layers? So all this happens. All this includes the magnetization of all magnetic layers become aligned in the same direction. Electrons with spin aligned opposite to the magnetization are scattered more strongly. The resistance of the material is determined by lower resistance in channel. All these are observed when a DC magnetic field is applied parallel to the base. Okay. Materials made of single domain ferromagnetic material nanoparticles embedded in non-magnetic matrix exhibit GMR. How does applying DC magnetic field affect the resistance of these materials? The correct answer is it decreases the resistance. Hybrid system exhibiting magnetoresistance property consists of, this is basically the option C, nanoparticles embedded in metal matrix sandwiched between metal magnetic layers. So we have discussed an example for this. We have seen this example where we have a metal which is silver and there are cobalt nanoparticles embedded on the metal matrix, that is silver matrix, and then we have magnetic metals magnetic metallic material which is nickel ferrite, that is, and these two layers are in a sandwiched manner. So this is an example for hybrid magnetoresistant materials. Okay, the phenomenon of magnetoresistance in metals is primarily observed under which conditions? So the phenomenon is generally observed under high magnetic fields and low temperature. Okay, and researchers are trying to make it in the other way. We are trying to observe these magnetoresistance at lower magnetic fields and normal temperature, room temperatures. Okay, so magnetoresistance effect become evident only when the magnetic field is stronger enough to curve the electron trajectory within a length equal to its mean free length. Okay, here mean free path. So it is the distance a particle travels before two consecutive collisions. Okay, which are with reference to GMR, consider the following statement. Magnetic resistance is the tendency of a material to change the value of magnetic resistance. GMR is used in hard disk drive. The correct option is option 2 only, because it doesn't change the magnetic resistance, it basically changes the electrical resistance of the material. Okay. What is the primary purpose of surfactant coating on magnetic particles in ferrofluid? It is basically used to prevent the particles from clumping together. Okay, or it will just attract and it will just stick together. To reduce that effect, we are using this some kind of surfactants. Which of the following is a common example for ferrofluid? The common example for ferrofluid is nanoparticles of magnetite suspended in oil. Okay. So ferrofluids are initially developed to, it is basically used to develop to control the fluids in space. Okay, it was developed by NASA and it was used to control the fluids in what is the fluids? We basically work on the uh, propellants or the fluids. Okay, so the next question is, yeah, next question is who credited with developing the first ferrofluid? The first ferrofluid was discovered by Stephen Poppel. Stephen Poppel was a scientist in NASA, and he was awarded a huge amount of money at that time. He was awarded around, say what I remember, he was awarded around $15,000 at that time. So it's a huge amount of money. Okay, okay, fine. So this is my Stephen Poppel. And how do ferrofluid responds to magnetic field? They change their density based on the strength of field. Okay. How do ferrofluids respond to magnetic field? They become, yeah, we have already discussed this question. So the effect described where linearly polarized light emerges as electrically polarized light due to application of DC magnetic field is known as cotton-Morton effect. Okay, so this was very well explained in the class where we use some kind of a laser source. We have seen the effect, right? I think we have seen the yeah. So we have seen that in the class. What is a technique that can be used to decrease the spin polarization of either electrons or centers in spin diode? Okay, the correct answer is electron um, ESR, which is electron spin response. Okay. So magnetic resistance. So what is magnetic resistance? So it is hard to describe. So I think there is no such term as magnetic resistance. It should be electrical resistance. See, there is no magnetic resistance. I don't think that is valid statement or something. So yeah, it should be electrical state, electric resistance. Okay, thank you. So this was the 30 questions that were described in today's class, and most of them were taken from the previous um, year assignment questions and also from some of the sources uh, from online and other sources. So yeah, thank you for listening. This is for today. We all can see on the next class. Okay. Thank you.